Today, what we'll look at is linearizing systems. On Friday, we looked at solving a linear system with the Laplace transform. And now we'll look at something that doesn't immediately involve the Laplace transform, but since we're talking about linear systems, it's kind of a good time to talk about this. And that is to turn a system into something that's linear or make it look linear and then investigate the behavior that way. It's actually much more geometric, but we'll get into that later. However, I do want to open up to any questions that you guys have. All right, I see a request to go over question 2 from Friday's online homework. That sounds good. Let me bring this up. Okay, looking at question 2 from day 25, for an example, I have one that looks like this: y double prime minus 3y prime plus 2y is equal to this piecewise defined function. It's 1 between 0 and 6, and then it's 0 for t greater than 6, greater than or equal to. You can rewrite this right-hand side using Heaviside functions. This thing here is going to just be a combination of Heaviside functions, such as this, where it is 0 up until you hit 0. Then after that, you jump up to 1. You're 1 for a while, and then after that, it's going to be equal to 0 again. And you can think of this as two Heaviside functions. One, let's say in red, that's going to look like this. This would be a u of t minus 0. And then the other one is going to be like this. Yeah, I mean for this red and blue to be 0 here, but I'm just trying to draw it so it's noticeable. Then this, actually, nope, not there. Here we go. That one's going to be u t minus 6. And you can see if you take the difference, 0 minus 0 gives you the yellow 0. And then we take 1 minus 0 gives us 1. And then 1 minus 1 gives us 0. In total, we can then write this as u of t minus 0 minus u of t minus 6. Then we can apply Laplace transform to both sides. And we also need this following information, which is y of 0 and y prime of 0 are equal to 0. And then applying Laplace to both sides, we get the Laplace transform of y times s squared minus 3s plus 2 is equal to, taking the Laplace transform of this will give us what? 1 minus e to the negative, actually 1 over s, and then e to the negative 6s. That's just applying Laplace transform to both sides. Then, of course, we can rewrite it, and we're going to end up with this. And now if I take this and put it on a new page, then what we get, if we rewrite it yet a little bit more, is 1 over s minus 2 times, or maybe I'll just write it all over one thing. We get s minus 2, s minus 1 times s, and then times this 1 minus e to the negative 6s. Now we can do partial fractions on this part in the square brackets. If you do, you can write that as a s over s minus 2 plus b over s minus 1 plus c over s. And again, that comes from partial fraction decomposition. Now, I'll save the solving of a, b, and c for now, just because it's something we've done many times. But more importantly, let's look at what happens if you knew what a, b, and c are. They're just some constants, so we'll just treat them as such for now. Well, you can think of this as two parts. You can think of it as everything in square brackets here, if we distribute the 1 through here, and then it's minus everything in square brackets times e to the negative 6s. Actually, maybe I'll put that in yellow to highlight the fact that it's going to give us a Heaviside function. All right. Now at this point, if we want to find the Laplace or we want to find y, we'll take the inverse Laplace of both sides. So again, let me put that on a new page. And I'm even going to make a slight adjustment here. I'm going to say e to the negative 0s, which is of course just 1. But in order to get it to match the form that it's stated here, where it's f of t times u of 0, g of t times u of 6, we're going to want to think of 1 as being e to the negative 0s. Now, when we take the inverse Laplace transform, the way to think of this is e to the negative 0s, e to the negative 6s. And just simplifying this for a moment, we can think of this as, let's say, f of s, and same thing here, f of s. Now, if we use, well, I think it's line 27, but let me double check. Yeah, okay, it's line 27. Using line 27 in the Laplace transform table, what we end up with is the first one, just really using the Laplace table, it's going to be u of t minus 0 times the inverse Laplace of this f of s, which is going to be a e to the, oh, I should have done 2 here, s minus 2, e to the 2t plus b e to the t, and then plus c. And then likewise, we're going to have minus, and now by the 27 again, line 27, we have u to the t minus 6. We have the same thing almost. We have a e to the 2 something plus b e to the something plus c. And now the something here is going to have to deal with this 6. Since we have minus 6 there, then we end up shifting this. So we get t minus 6, t minus 6. And you might ask, well, why? Well, that's exactly what it gives us in the Laplace table on line 27. It says you have to shift whatever you would have gotten here by this amount. And then fitting, like matching this up with the problem, this would be your lowercase f of t, and this is your lowercase g of t. So that was the second question of day 25. All right, looking at some of the other questions people had. So there's numerous questions on written homework 5, so let's look at that. And someone also asked about written homework 4, and I'm just double checking, did you really mean written homework 4, or were you thinking 5? But I'll certainly go over 5. Okay, so let's look at written homework 5, which I think will be very similar to what we're looking at today anyways. But let me bring it up. Yeah. So written homework 5 is essentially trying to walk you through what we'll be looking at today. So you'll notice, so maybe what I'll actually do is, unless there are other questions, I'll lead that into our lesson, because going through the lesson today will explain exactly how to do everything from written homework 5. So the point of this homework was to kind of introduce you to the ideas beforehand and then help reinforce it today, but we'll kind of do it the other way. So this is what we have in written homework 5. This is not a linear system because we have an x times y here. And as soon as we have, x times y or x squared or y squared or something like that, it's not linear anymore. What it says to do in the first part is to begin by writing dy dx is equal to dy dt over dy dt, or dx dt. And then I think we went through this a previous time, but long story short, you're going to end up with a separable differential equation that looks something like this. And I cannot remember exactly, but you're gonna, I don't want to go through all this process right now, but you're gonna get to a point where you have y to the fourth. If you do this, yeah, and this may not be exact, but something like y to the fourth x cubed is equal to c e to the, was it like x plus y or something like this? Something approximately like this. There's a point where you end up with natural logs, but then you can put those in the exponent spot of e and then get to an expression like this. You can then use the initial value data to solve for this parameter c, or maybe you call it c1. So you'd substitute in and say when t is equal to 0, at that point in time, you have that x is equal to 2 and y is equal to 1/2. By substituting those in, you'll be able to solve for c, or c1 in this case, because the only thing unknown will be c and everything else will just be some numbers. Then from there, what you're asked to do is find an equilibrium point, which we'll talk more about today. That is a point where this is 0 and this is 0, which is not too hard to find. So you'll find two different points. In this case, I think the 2 points end up being, I think 0, 0, and let me check quick. 3, 2. Yep, 3, 2. Then what you're asked to do in, let's say, part D and E is, well, essentially graph what you get here. I can't remember what C1 is offhand, but it's some number. You can take and graph this as an implicit curve in Desmos. Just, go to the implicit graphing portion of Desmos. This will end up being, once you have the specific C1, that goes through this value, I think you'll end up getting a kind of ellipse type thing. So you'll end up with something kind of like this, where it passes through this point that is 2 and 1/2, something like that. Actually, let me color that different color. So it goes through 2 1/2. And then if you look at the equilibrium points, or the equilibria, you'll get, I think, something like this, and then something like this. And then what you're asked to do is to describe how this behaves over time. And essentially, the long and short of it is, I can't remember if it's clockwise or counterclockwise. You can do a check by looking at the slopes around it, but actually just by plugging in the point here, 2 1/2. Actually, let me check really quick. 2 1/2. So it's positive, and then 2 1/2 will be, let me do a quick check. 2 1/2 minus 3 1/2. So 1 minus 3/2. So it's going to be negative. Yeah, okay. Yeah, so it looks something like this. And the idea is, over time, what's going to happen is that the respective populations are just going to kind of circle this equilibrium point and essentially kind of swing around this equilibrium point, come back and sort of swing past this equilibrium point and so on, and just kind of run around in this oval type shape or ellipse type shape. That's the behavior. And actually, we'll look at today how you can investigate what's going on around points like this a little more using linearization. So let's actually do that. Let's jump into linearizing systems. Okay. So I've written a bunch here and I'll go through it. Say we have, to begin with, some function just of t, and it looks like this. It's not the worst function in the world, but it's not the nicest function in the world either. If we wanted to linearize, let's say from Calc 1, the idea is if we graph this function, let's say this is cyan, and the graph of it looks like that around the point 0,4, you can plug in 0 into this for t and then find out that you get 4. So it goes to the point 0,4. If you look around this function, and I think it goes off and does behavior something like that beyond. But if you just focus on a little neighborhood around it and you zoom in close to this thing, what this will end up looking like, again, once you get really, really close, is it essentially looks like a line. So you've got your point here, which I'm trying to draw bigger to make it seem like we're actually zooming in. And then you've got the line here, or the curve. And when you're really close, it basically just looks like a line. If you do this with any function, you just go ahead and zoom in on, let's say, Desmos or any graphing utility. You'll find that no matter what point you pick, if you just zoom in and zoom in and zoom in for a while, eventually you're going to, and you keep it focused on like one point, what you're going to find is that it eventually will look indistinguishable from just a straight line if you zoom in far enough. And that's where the idea of linearization comes from, is we can think, at least locally, that any function just looks like a line if you zoom in far enough. You may have to zoom in really far or not so far, depending on the function. But the point is, zoom in far enough, and eventually it looks like a line. So to linearize, you can take something that might be very complicated, or at least kind of be a pain to compute, and you can turn it from something like this into something that's very easy to work with, just a line. A line is like, one of the simplest functions we could have. So in order to do that, we essentially look at the tangent line to that curve. We want the function f of t to basically just look like a line, which is some mt plus b, where t, of course, is replacing x here. And I'll just, switch the order of this. But we could write this as the intercept plus the slope times the independent variable. Or alternatively, as the starting value, x naught, which would be 4 in this case. 4 is x naught, plus the slope times the change in the independent variable, t. That is the point slope form, where you have a point, t naught, x naught, and then you have a slope m. And you can convert between the slope intercept and the point slope. Of course, they're just different ways to write it. But the point slope form will be the way we think about linearization. What we want to do is, this should be approximate. We want to think of f as approximately equal to this point slope version of the line. So we take x naught to be the starting x naught, which I've put in red here. That would be, in this particular case, 4. We take the, that should actually just be t naught. We take the slope at the given t value. So we look at, in this case, a t value of 0. We look at the slope there. Again, if we were to go to a different t naught value, we would have a different slope that changes as you look at different t values. But here it's going to be, I don't know, looks like, I think it's 2, but it looks like roughly 2. And then we take the starting t value, the difference of that with t. And again, this is exactly just the point slope form. Notice I can line it up exactly here where m is just the derivative. This thing over here is exactly the tangent line. And let me really stress that, or equation of the tangent line at that point. So this is just equation of the tangent line. That's it. The linearization, again, is just the equation of the tangent line, and we call it linearization because we're literally just looking at lines. So it's linearization. Now, again, as I stressed before, this is a local thing. When you go through all this process, what you're doing is you're just looking at the function around a given point, namely 0, 4. If we were to suddenly jump over to, I don't know, let's say t is equal to 100, that line would have, gone off like this in both directions, and maybe the curve itself, or the function itself, would have kind of been like, oh, not that, autocorrect, would have kind of been like that or something. So when you're at 100, it's like, not even close to where you want it to be. So again, this only works when you're looking locally or really close to a given point. If this makes sense, then the next things we look at should also make relative sense, because we're just going to be doing this essentially twice instead of once, and be doing it with partial derivatives. But otherwise, the idea is exactly the same. Now, to summarize what the whole point of this was, we took this cyan function and we said we want to linearize it. So we find the derivative at a particular point. So near 0, 4, or in particular, when t is equal to 0, we have that the derivative of this function is just equal to 2. So again, when we're near 0, 4, we can write it this way, where this is, maybe let me write it like this. This is our starting point. And what we end up with is that f of t near 0, 4 is just going to be 4 plus 2x, which is, or 4 plus 2t. So we have a much simpler function, 4 plus 2t, compared to all this here. And if you only need to look near a given point, well, then this could be all that you need. You may just need to know approximately what's it going to look like. And it's much easier to work with. You can investigate what's going on here much more easily than you can investigate what's going on here. And like I said, if this makes sense, then the next topics that we'll start to look at, I think, won't be too bad. But either way, we'll get through it. So now let's talk about what points we would actually want to look at. In particular, if you've got, let's say, a linear system, or not a linear system, just a system of Diffie-Qs in general like this, where dx dt is some function of x and y, dy dt is some function of x and y. We want to look at particular points, and they're exactly the equilibrium points that you would have found in that homework. So here we're looking for equilibria. I can't remember if it's 2 L's or 1. But what we're trying to find is some point such that when you substitute it in, x naught and a y naught, what you get out is 0 in both cases. This is just like what we talked about in the homework. The claim is then that the constant solution, x is equal to x naught, because remember, x is a function of t, so it could have a t involved, but if we just set it equal to this x naught constant, and then we do the same thing for y, just set it equal to this y naught constant, the claim is it's a solution. And why is that so? Well, if you take, by definition of finding equilibrium, if you take f of x naught, y naught, what you should get is 0. That's because it's an equilibrium point. And then if you take g of x naught, y naught, you should also get 0. Okay, that's one side. But if you take d dt of just a constant, namely, let's say x naught, what you'll also get is equal to 0. And of course, d dt of y naught will give us 0 because they're just constants. So it's a solution. It satisfies the differential equation. In both cases, we get zeros. Actually, maybe I should put these in red here. So what we're going to do is we're going to find equilibria, and then we're going to do the linearizing, the thing that we just reviewed for single variable functions. We're going to do that around each equilibrium. Suppose we, again, have our system here. And what we're going to do, like I said, is linearize around these equilibrium or equilibria. So I'm trying to keep the equilibria in red here as a reminder that these are points that we found in particular, particularly nice points. So let me maybe even remind us that this is equilibrium. Now to linearize a multivariable function, it's not too much different. And actually, I'm even missing some parts here. Let me fix that, and then I'll talk more about how it compares to what we've already seen. So this is x minus x naught and y minus y naught. All right, in the single variable case, let's see if we can see how it's similar. With the single variable case of f of t, what we did is we got f of t naught plus the derivative of f with respect to t of, so the derivative with respect to t of f at t naught times t minus t naught. Our starting value in this case was here, which I'll put in this red color, similar to the equilibrium points. And now let's see if we can match this up. Well, we notice here, there's sort of a starting value, as it were. So quote unquote starting value. Then in the single variable case, what happened? There was a slope. And then we multiplied by a change in independent variable. We have the same thing here, in the multivariable case, except that we now have more than one variable. So there's a slope for x and then a slope for y. But in each case, we do the same thing. We have a slope times the change in the variable. And we just have to do it as many times as we have variables. So here's a slope, but now for x, and then a change in x. Likewise, there's a slope for y, and then a change in y. Idea, exactly the same. With the single variable case, we get a line. In the multivariable case, we don't get a line. Actually, I'm curious just to see what you remember or guess. Do you guys know what shape this is? If this is a line down here, like you have a line like so, do you know what shape this is? Maybe, maybe not. Yeah, it'll actually end up being a plane. It'll be something kind of like this. So it's a plane in three-dimensional space, but it's just a higher dimensional analog of a line. Instead of a line, you have a line of lines. Now, if we do the same thing for g, what we end up with is g of xy is approximately equal to, now again, follow the formula. Even back in the Calc 1 case, you have a starting value. Well, your starting value is going to be g at a certain spot. Then we're going to add to that slope of variables times the change in the variable. So we have slope of f with respect to x times the change in x. And then we have the slope of f with respect to y times the change in y. And we're always substituting this initial point, this equilibrium point. And I could write all this again, but it's going to be the same thing where we have a starting value, a slope for x, change in x, slope for y, and change in y. Which, just to really emphasize the point, we have a starting value down here, slope, change in the independent variable. All right, well, that's fine. So let's maybe look at how we can use this or look at a specific example. And yeah, let's maybe start with like, how do we use this type of thing? So if you have a linearization, and let's maybe put this like so. So say we've taken a nonlinear system and we've linearized it. So now through the linearization, which must be done near x naught, y naught, which you get is, let's say, dx dt, dy dt is something like so. I'll maybe write it ax or alpha x plus beta y, because that's a general linear form. And then for the other one, let's say we have gamma x plus delta y. What you can now do is look around x naught, y naught, and plot slopes. So you would take the point x naught, y naught, say it's here, and then you can plot slopes around it. And let's see, how do I want to say this? Yeah, we'll look at it in a more specific example in a bit and see how one can do this methodically. But the idea will be to look around this point and then look at the corresponding slopes. For instance, you may have that over here to the right of the point, if you look at your change in x with respect to t, you get something like this. And then you may have something like this for your change in y with respect to t. And then maybe over here, it goes like this and like so. At any given point, you can plug in a value, xy, and see what the corresponding change in x and change in y look like. So over here, you might have maybe this again. And then something like this. And then over here, you have this and something like this. And then if you look at the overall slope, you might have something like that, something like that, something like this, and something like this. And then if you do that for some more points, you might get something kind of like so. So what you can then do is say around this point, this x naught, y naught, it wasn't clear from the color. Again, this is x naught, y naught. You can look at the behavior around that point, and it can tell you about the system itself. And there's a few different possibilities of what could happen around that point when you're looking around an equilibrium point. So here are kind of the 6 main possibilities, and you can have slight variations of this with some kind of wiggles, but largely it's going to look like this or look like one of these. You could have an equilibrium that pulls all the solutions in towards it. We call that a sink. You could have one that pushes everything out, call that a source. You could have one that sort of pulls in from one direction, pushes out from another direction. That's a saddle. But instead of having a sink where it just pulls everything more or less directly in, you could have things spiral around and move towards the equilibrium point. You could have it spiral out away, or you could have it just circle and not neither be pulled in nor pushed away. And someone asked the question, is linearization meant for creating local slope fields? Yeah, yep. Essentially, that's a good way to put it. Linearization in this context used to create, I like that phrasing. And maybe instead of, I almost don't want to say slope fields exactly, but maybe I'll say directed slope fields. The reason it's not just slope fields, period, is because if I jump back to this previous page, you'll notice that you can do things like this where you can go to the left. But it's not quite a vector. Actually, I guess it's actually a vector field because you do have magnitudes. So yeah, it's directed slope field. If it didn't have magnitudes, then it would be directed slope field, but I guess even vector fields. Though all we'll really care about is the direction. We won't actually care about the magnitude so much. Okay, good question. All right, let's look at this in an actual example and see kind of what's happening. Say here we've got our linear system, and this should look very similar to the homework. Actually, oh man, it's exactly the same. Okay, fair enough. Actually, let me see how much I said earlier. I'm going to jump back. Yeah, okay. So you were asked to investigate this without the linearizing, but now we can use the linearizing to investigate it in a different way. Actually, do I want to do this, or yeah, let's do this. Then we can do another one if there's time. If we go about finding the equilibria of this, it ends up being we have 0, 0, and let me do a double check. 3, 2. So around each point will linearize, and we get this kind of local effect. Let's start by linearizing around 0, 0. I'll take this and I'll do it on a new page. So we're going to linearize around 0, 0. Okay. For this function here, if I call this, let's say, f, to linearize around 0, 0 for that function, what we get is f of xy is approximately f of 0, 0, so the starting point. And then if we remember from the linearization we looked at in all the previous examples, it's always your starting point plus a slope times the change in the independent variable. And you just have to do it as many times as you have an independent variable. We have 2 here, so we'll do it twice. We take the partial of f with respect to x times the change, and then the partial of f with respect to y times the change. All right, that will amount to f of 0, 0 is simply, I think, going to be 0. The partial of f with respect to x, maybe a little side calculation, partial of f with respect to x is going to be equal to 4 minus 2y. And then we're going to have y is equal to 0. So when we're at 0, 0, what we end up with in that case is just going to be 4. So we get the slope is 4, and then we get x minus 0, which is just x. Then we have partial of f with respect to y is going to be equal to x minus 3, evaluating that at 0, 0. Oh, nope, wrong one. With respect to y is going to be negative 2x. And then that, of course, will be 0 when evaluated. So in the end, we just get that f of x is approximately 4x when you're around 0, 0. Do the same type of thing for y. So linearize around 0, 0, but do it, or not for y, but do it for this function, which maybe we'll call g. I'm going to erase this work for the moment. We'll get g of xy is approximately, I'm just going to kind of jump through these quick. We get 0 plus the partial derivative of this with respect to x, I think is just y at 0. It's going to be 0 And then the partial derivative of this with respect to y is going to be x minus 3. So I think we'll get minus 3 times y. So negative 3y. Now we have in the end that our linearization is dx dt equal to 4x. And then we have dy dt is equal to negative 3y. Sometimes I kind of like to space them like this so we have the x column and the y column, but either way. Now, we've linearized around 0, 0. Let's take this and use it to investigate what's happening with the system around that point. So we linearized around, actually, let's do this here. Around this point. We end up with this system. Now let's take and kind of investigate what's happening. So if we look at the point 0, 0 in this xy plane, for points near 0, 0, we're going to have behavior determined by this system. So let's see. If we have the point, let's say here, and it's small x value 0, y, what we'll notice is the change in y is nothing. And then we get a positive change in x. At that point, I'll draw this little vector. I'll draw something like this. Then if we look at, suppose, this point, where both x and y are positive, what we have is that the change in x with respect to time is going to be positive. Meanwhile, since y is positive, the change in y with respect to time is negative because we have negative 3 times a positive. So we get something like this. And if we do this for a couple other points, maybe we kind of just do a little grid. Like this, and we fill these in quick. I think here we're going to have no change in x. Here we're going to have positive. Here we're going to have negative, negative, negative. And then this will be negative, positive, something like this looks like. Right. Now we fill in the arrows, which I'll do in white here. So we have this white arrow. We have white arrow, which is the same as the yellow. We have this. We have this, and so on. Now, if we kind of imagine what's going to happen, the solution curves around here, well, if you are already on the y-axis and you're below y is equal to 0, so you're negative, what's going to happen is you're just going to follow these arrows upward and get something like this. Actually, let me draw this a little thicker. Get something like so. If you start above and stay on the y-axis, you'll get something like this. If you are on the x-axis and you're positive, you're just going to move away. Same thing here, move away. And then you'll see this after you look at enough of these graphs, but the idea is you're getting pulled down here, and then it sort of transitions to getting pushed away. So it looks like this. And likewise here. Likewise here. And then finally here. So this is an instance of what we call a saddle point. So we say 0, 0, which is the equilibrium of this system back up here. We linearized it, and then we use the linearization to investigate what's happening around this. And what ends up happening is this is a saddle point. So now I want to open up to, questions you guys have about this. Is this making sense? Is it not? I'm not sure if it's maybe very easy and seems obvious, or if it's somewhat challenging. So what are your thoughts? Okay, got a few comments. Thank you to those who gave some comments. People are saying it seems to make sense, so that's good. But if not, just let me know. I do want to say you could do some similar investigation here, even without linearizing, namely because these formulas are not too complicated to work with. But especially when your system is much more complicated, much less linear, as it were, this certainly can be a lifesaver because you're simplifying down to what's pretty easy to work with system. All right. Let me check and see if there's anything else I want to say about this. No, honestly, I think that's it.
To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.